Okay, next up is Jonathan. All right.
Sorry. Let me turn on
the
share screen.
All right. Yeah, it works. So yeah, the next speaker is Jonathan Heckman from University of Pennsylvania, and he will tell us about a life without holomorphy.
Actually, sorry. It looks like my my Mac is dying. Let me actually switch to my other computer.
Okay.
I don't know. It's of course perfect timing, yeah.
Of course.
Hi, you see me?
Yeah, you have to just mute one of the.
Yeah, I already muted. Oh no, I didn't.
Right. Yeah, no.
I really hate Zoom conferences, but anyway. This one's awesome though.
Right.
Okay, so yeah, let me first begin by saying thanks very much to the organizers for putting all this together and for giving me the invitation to come speak here, at least virtually. So many thanks to the organizers. I already said this. You know, it's especially great that there's at least one big annual conference which is devoted to topics closely connected with string theory. As opposed to other conferences that have the word strings in the title, but have 10% or less on strings. Okay, so enough of that. So thanks very much. And here are some facts of life. We haven't seen any super partners yet, although you may imagine that they will appear someday, maybe soon. The other fact of life, at least when we're talking about doing computations, especially in the context of string theory, is that the situation is so technically demanding that we often rely on supersymmetry to have exact results of some kind. This, of course, makes it very difficult to do things without supersymmetry. And usually this is a catch-all, as you've seen from many of the talks already, that when we talk about supersymmetry, what we really mean is, or in the context it's typically applied, we mean in the context of using various kinds of holomorphic structure. So, the main idea of the talk is I'm going to try and see what we can extract from string compactifications or string theory considerations, just relying on anomalies or kind of topologically robust structures. Now, this is a very old idea. Anomaly cancellation, of course, famously in what caught a lot of excitement in the first superstring revolution. But this has continued to be refined, and as we just saw in talks today, even that refining this can provide many powerful constraints on how we think about strong coupling dynamics and also what we think about as string. Okay, so I'm going to try and compute in situations which have little or no supersymmetry. And so in particular, no holomorphic structure.
Jonathan, sorry, could you come a bit closer to the computer? It seems the sound is partially breaking off.
That's why I was on I've got an idea. Let me do this. I will mute myself on this one. This is. How about this? Okay, how about this? Is that better?
Yes.
Okay. So hopefully, yeah, I have two computers and I only get like half of contribution from each one. Okay, so this is interesting for, so why would you do this? Well, how well is the landscape understood in diverse dimensions? Also, little is known about string compactification without holomorphy. And also, this is interesting for its own sake. So I'm going to do this basically focusing on two examples. And so here's the plan of the talk. I'll give you two examples that illustrate these things. Number one is going to be about a background that has supersymmetry, but it has no holomorphy in the conventional sense. So it's going to be three-dimensional, n equals 1 vacua as obtained from M theory on a spin 7 background. So two real supercharges. And then the next example is in some sense even more basic, I'm going to analyze kind of some non-holomorphic structure associated with type 2b and its famous duality symmetry. And what I'm going to try and do is compute for you a very subtle topological anomaly associated with this thing. Okay, and then I'll just wrap up with kind of conclusions in the future. Okay, so this is based on the following sets of papers. So some of these have already appeared, and some of them will appear hopefully relatively soon. And there's also some background stuff. And I'm sorry if I missed referencing your paper, or so anyway. Hopefully the references are more complete in the papers themselves. But if they're not, please just let us know. Okay, so let me begin with the first example, 3D n equals 1. So this is something that appeared relatively recently. So, okay, so in the context of string compactification, in particular M-theory compactification, as we go down and go on various higher dimensional spaces of special holonomy, we reduce the number of large macroscopic dimensions and also reduce the amount of supersymmetry. So we can go, so Calabi-Yau compactification is of course a very famous example of this sort. But of course we can go all the way down to lower ones. For example, famously G2 compactification gives us 40 n equals 1 backgrounds. And I'm going to be focusing here on the case of M theory on spin 7. So 3D vacua with 2 real supercharges. Okay, so 3D n equals 1. So this is an interesting place to look for things because it's supersymmetric. So we have good indication that we expect the background to exist. On the other hand, it's non-holomorphic. So it's kind of an intermediate choice to take. There's a real spinner here, and that's the real issue with this. It's also related to more speculative work on looking at F theory on so-called n equals half 4-dimensional backgrounds, although I'm not really going to focus on this at all. Finally, there's a lot of work that was done earlier on basically trying to see what kinds of 3D field theories you could get from M theory compactification. And I won't make so much contact with this, but it will of course be lurking in the background. Okay, so at the classical level, here's what we would do, as we would commonly do in string compactification. We would write down compactification on some 8 manifold. That's our local spin 7 space. And the one I'm going to take is going to be a 4 manifold of ADE singularities, given like this. And based on what we understand about how M theory on singular spaces works, we expect this at long distances to be described or well described by 7-dimensional gauge theory with a gauge group of ADE type, wrapping the 4 manifold and filling the 3-dimensional space-time. And in fact, there's a type 2A way of making the same kind of thing, at least when you restrict the gauge group to be of A or D type, which is to consider the local G2 space given by a bundle of self-dual 2 forms over a 4 manifold, and then just wrap D6 branes over the 4 manifold and then have them fill the space-time. Okay, so classical backgrounds. So I'm not going to go into too much detail here, but again, just using the type 2A picture, you can see that we have these 6 branes, and we can consider intersections between them. And generically, actually, they will tend to intersect over 1-dimensional subspaces inside of the 4 manifold. So matter is generically on a 1-dimensional space. You can kind of tune the system so that it's actually on a 2 real dimensional subspace. But for the purposes of what I'll do today, I'll mainly just focus on the most generic situation. Okay, so that's the kind of classical geometric picture. And there's a very nice way to analyze all this using the mathematics of Higgs bundles and kind of the unfolding of singularities associated with this structure. Okay, now quantum mechanically, again, because there's basically no holomorphy at all in this setup, you can ask, okay, well, what happens at the quantum level? Do we get large corrections of some kind? So what I'm going to do is I'm going to try to study this via anomalies involving space-time reflection symmetries. So the subtle point here is that because you have such low supersymmetry and you're in such low dimension, it becomes very difficult to kind of extract what's going on in deep infrared for these kinds of backgrounds. So what we're going to try and do is use topological features of these backgrounds to see if we can at least detect some aspects at long distances. Okay, so here's a definition of what I mean by reflection. We're going to take the 3 spatial coordinates. I'm going to mainly work in Euclidean signature, so x0 is for me Euclidean time. You can, of course, analytically continue back. And there's different notions of reflection you can talk about. Here I'm just taking spatial reflection on, say, one of the coordinates, this coordinate 1. Okay, so scalar can reflect in this way. Pseudoscalar has an extra, I'll just refer to this as something that has a minus sign. And then for me, the fermions are going to have these choices of phases. This is a gamma matrix, a 2+1 dimensional gamma matrix for the 3D theory. You can insert other phases, but for the topological structure I'm talking about in particular, putting it on pin plus spaces, that'll be good enough for me. Now, by tuning, you can show that actually by tuning the moduli of this 4-manifold, reflections of, say, the 7D theory defined in flat space can actually descend to 3D reflections. So at kind of the classical geometry level, there is a chance to retain some of these reflections in the compactification. Okay, so I'll refer to this as the gravitational reflection anomaly. So you might say, why are we talking about anomalies? We're in an odd dimensional space. Well, that's sort of true. There's no kind of nice continuous anomaly, but we can still track what happens to, for example, the partition function of the 3D theory after applying one of these reflections. And it can pick up a phase, which I'll refer to as nu sub r, r for reflection. And it turns out that this is given by some mod 16 condition. So for example, I'll refer you to some of these condensed matter papers. There's a very nice exposition more for high energy theorists here. And the way to visualize this, so the fancier way to think about this is to visualize the 3-manifold where the quantum field theory lives is kind of being inside the interior of a 4-manifold which has been cut open. So we kind of join this back together, this 4-manifold and 4-manifold prime, to make some bigger 4-manifold. And what we're really doing is computing at some level some topological theory on this 4-manifold, and then trying to extract a phase from this. So this phase here is closely related to an eta invariant on this big 4-manifold. And again, for the kind of super familiar people, the thing I'm using here is that there's a Bordism group, and it's going by a mod 16, integers mod 16. Okay. So let's compute this thing. So the purpose of our paper was actually to see whether we could compute this in these local models and actually extract this information. So if we consider intersecting 6 branes wrapped on these 4-manifolds, one can actually show that the this anomaly, this nu, splits up into a bulk piece and a local piece. The bulk piece is just controlled by everything that's not localized. It's kind of still spread over the entire 4-manifold. And it descends basically, the reason why this thing is appearing here is that all of those things are in the adjoint representation of the unbroken gauge group. And it depends on the Euler character of the 4-manifold and the signature. And again, it's a mod 16 thing. This is a bit different from what we would have, say, in a 4-dimensional background where we might try to count things according to integers and so on. But here, the best we can do is really a mod 16 at kind of the fully quantum level. Similarly, for that localized matter I told you about that's trapped on 1-dimensional cycles, it kind of splits up into 2 pieces, those that have kind of a plus reflection and those that have a minus reflection. And again, this is actually directly tied to the geometry of the Higgs bundle and how exactly the matter got trapped. And so there's an overall plus sign and minus sign with that localized matter. And again, you can just count these things and you can just sum them up. Okay. What's the value of this thing? If you have a model and you find that nu sub r is not equal to 0, then even though we may not know very much about the strong coupling dynamics at very long distances, we'll know that something survived in the infrared. In fact, even in cases where this thing vanishes, as you might expect would happen if you ever kind of try to recouple to gravity, one can show, based on the structure of the local model, that at least locally, all the matter kind of has the structure of being topologically protected until you compactify and make the 4-manifold compact. And so what that provides you with is a notion of saying that there's actually a hierarchy of scales, and that far below the Kaluza-Klein scales where you actually start to pick up these strong coupling effects. So again, we can kind of start from that UV quantum field theory, and then track at least some pieces of it before it hits the deep infrared. Another comment I'll make is that there's another anomaly related to reflections, this one about reflections and gauge transformations. And actually, in some cases, what you find is that it turns out to not be 0. This actually turns out to be a mod 2 condition. And when it's non-zero, it actually detects the presence of a half-integer 4-form flux that has to be switched on through the ambient 4-manifold. So these are the kinds of things that we can actually kind of reliably extract from this. Okay, so let me give some examples. So a very kind of, by this point, classic construction of for the n equals 1 vacua in the local M theory context is to take M theory on local G2 space. And we can think about this as 7D Yang Mills wrapped on a 3-manifold as opposed to a 4-manifold. I don't know if I got all the references, but anyway, that's some set of them. So you can start from 3D n equals 2 just by wrapping on a circle, and then you can actually break n equals 2 supersymmetry by just start gluing in just generic four manifolds which don't have any localized matter of any kind. So when you do this, the anomalies start to shift, and you can actually track it in terms of some inflow that's going across kind of tubes. This here is a kind of locally a gluing of a four ball. You can write down like basically a local Euclidean wormhole metric, which connects this bulb to this bulb. But the point is that there's a gluing construction available. This blue line here is supposed to represent some localized matter. And of course, there can be many examples of that sort. And so in these examples, you can, of course, just start reading off the value of nu sub r, which is one of the things we do in the paper. As an example, you can take a 4D gut and then start gluing it and making it into a 3D thing. And this, of course, follows this pattern, as Laura kind of briefly hinted at in her talk, of taking E8 and unfolding it in the following way to some SO10, and then the adjoint representation of E8 breaks up into representations of SO10, which are in the adjoint of SO10, the 45, the vector, the 10, and the spinner, the 16. Now, a fun fact about this particular case is that the spinners automatically contribute nothing to this nu sub r, because 16 mod 16 is just 0. And so all you're left with, it turns out, is these 10s. The reason for the 4 here is because you have to remember to count this thing as a complex representation. But anyway, that's a small point. This is kind of the number you can extract for these kind of models. So we have examples of that sort in the paper. Okay, that's the first example. So what did I do in that example? I showed you some examples of what you can do with topology to start constraining the structure of system string compactifications where there is some supersymmetry still, but there is no holomorphic structure to kind of fall back on in many cases. Okay, so let me now move on to the next example. And this one's about type 2, or for me trying to be clever, 2B. And it's about an anomaly in that theory. Okay, so here, this is another famous fact, type 2B string theory. We know it's been known for a long time that type 2B supergravity has an SL2R duality group. And if we look in textbooks, the usual statement is that this thing is broken to an SL2Z by the presence of branes and flux quantization, if you like, and so on. Okay, now this actually isn't 100% correct for the simple reason that we're neglecting the transformation rules on the fermions. So a slightly more precise version of this is to talk about so-called metaplectic cover of this on this SL2Z. And this just has to do with tracking the duality transformations on the superpartners to the dilaton and the graviton, so the dilatini and the gravitini. I'm sure there's other references here that I'm missing. Sorry about that. But in fact, even this is not the end of the story. It turns out that if you then demand that M theory and F theory duality really functions correctly, one also has to allow for various kinds of orientation, flips, and reflections that we know make sense on the M theory side and therefore are required at some level on the F theory side. And this actually pushes you all the way up to the so-called pin plus cover of GL2Z. Here, pin plus is kind of the signal that we're talking about something having to do still with fermionic degrees of freedom. It turns out also that the chiral 4 form of 2B also kind of non-trivially transforms under this thing, basically by a minus sign under some of these reflections. Okay. I'm going to focus on this one because this seems to be the full-blown thing. And what we're going to try and do, so this is only recently been written down. What we'd like to do is just ask, okay, what about anomalies for this thing? Do they vanish? Is that guaranteed? Or are there issues with this? So is type 2B duality anomalous? So I'm going to follow the same strategy I did in the previous section where I had a 3 manifold and I viewed it as kind of basically being something that got cut, was being cut from one higher dimension. And so there's kind of a topological theory we can write in 11 dimensions such that if we cut it open, we expect to get back out type 2B. So what we're going to be doing is computing some topological quantities associated to this 11-dimensional auxiliary anomaly theory. Here it is. This involves a bunch of topological stuff. The idea is that we have this duality bundle. So we're imagining equipping this with some non-trivial SL2Z, or more precisely GL plus 2Z bundle. And I don't really have time to go into the details of all these things, but just to summarize, these pieces here, this is RS is for Rarita Schwinger. This is associated to, if you like, a spin 3 halves or Gravitino type thing, but really it's shifted by a background Dirac fermion. That's all the Gravitino stuff. There's a dilatino contribution, and then there's a bunch of contributions all having to do with the chiral 4 form. So the particular subscript 1 here refers to the charge of these things. If you imagine embedding this thing inside of some of these transformations in terms of a continuous charge, just tracking the charge of these gravitinos and dilatinos. These pieces here, this 8n variant is associated to the Hirzebruch signature. This is the ARF invariant. It depends on some kind of quadratic refinement, and this also depends on a quadratic refinement. I'm not going to talk too much about these, but basically the short answer is that all of this is kind of where the chiral 4-form data enters. And you have to include this in order to completely calculate pieces of the anomaly theory. I should also say I'm going to neglect everything to do with the RR2 form and NS2 form. So all the backgrounds I'll talk about have that thing switched off. Okay, so does the anomaly theory vanish for all M11? So if it does, then we have a good piece of information that yes, anomalies cancel as we would expect, because we all know that 2B string theory is okay and F theory is great and it's all wonderful. In fact, the answer is no. It turns out that if you compute this thing for explicit choices of this anomaly theory, you find that it is non-zero. And so something is going, something strange has happened. Okay, so how do you compute this thing? So the relevant quantity here, I'm just going to summarize it as omega 11 duality. There's a Bordism group calculation that one has to do, and it turns out that there's a bunch of little pieces, all these different generators. And basically the idea here is that different choices of M11 correspond to different choices of these generators. So what we need to do is pick a representative M11 for each one of these and compute the anomaly theory on each one. Okay, now the good news is that actually a lot of them just have vanishing anomaly theory straight up, so there's nothing to worry about. But it turns out that for some of them, it doesn't vanish. Notice also that I'm not even bothering telling you too much about whether this thing, would retain supersymmetry on the boundary or whatever. That's not the question here. It's more a topological question here.
Okay. Yes, 5 more minutes.
Okay, thanks. So, okay, this thing seems to have some non-zero anomaly. So what does that mean? Does that mean that type 2B duality is anomalous? If that were true, then it wouldn't just impact type 2B, it would impact kind of the entire duality web. And these things are also tightly linked. So once you remove one of them, it's basically like the whole structure would start to kind of inevitably collapse. So probably this isn't true because obviously, there's a huge amount of evidence for these things. So probably not. But then the question becomes, okay, so what? Why is it? Why is it not a problem? Or how do we get around this? So let's talk about how to fix it. So amazingly, it turns out that you can add one more topological term, a very subtle topological term, to the ordinary 2B action, which, there's no reason that you would have detected it using any of the previous analyses. So it's very obvious, it's very clear that it could have escaped analysis before. And it involves, here, this is the 5-form field strength from Ramon 4-form, chiral 4-form potential. And it involves discrete analogs of various kinds of fluxes associated with kind of the duality bundle. The reason for the Z3 and the Z4 has to do with the particular structure of SL2Z and its lifts into GL plus 2Z. Let me not get into that too much. Morally speaking, A is just, little a is just a connection, little b is just a connection. And this thing here, this frac FA squared can be thought of, so frac FA can be thought of as like a field strength built out of A. It's a 2-form, and then we build a kind of 4-form out of that. P1 and P1 here is just a Pontryagin class, and this little subscript 3 just means reduce the thing mod 3 or reduce the thing mod 4. And this is just something built out of the Stiefel-Whitney classes. Anyway, so this is a thing. It kind of looks like a Chern-Simons term of some kind, but the magical thing about adding this Chern-Simons term, it's very analogous to the usual C4 wedge B2 wedge H3 thing we typically have in 2B supergravity. But adding this one term allows for all the anomalies that we talked about for this other theory to just cancel right off the bat. Okay, so let's do a couple cross checks. So I'm proposing this new term, or we're proposing this new term. Does it pass any tests? So in fact, if you write down, there are known backgrounds in type 2B involving so-called S-folds. These famously appeared in the N equals 3, 4D N equals 3 field theories that were written down in this paper, and also kind of in these more stringy, or in these other versions, where they were kind of recognized, I think, as like S-folds in particular. They're just some non-perturbative generalization of an orientifold plane. And if you take this thing, you can ask, what's the D3 brane charge associated to it? So you actually get some torsional background, and you can predict what the value of that fractional background is going to be from this kind of topological term. And it predicts in particular that S-fold charges go in units of things like 1/3 and 1/8. Here's another check. You can take type 2B strings on ADS5 cross S5, and if you reduce on the 5 sphere, there's n units of 5 form flux going through this thing. You pick up this kind of thing. So this kind of predicts that there should be some kind of duality anomaly for the boundary n equals 4 Yang-Mills theory. And indeed, there is. So if you consider kind of the 4-dimensional theory and you ask what happens under duality transformations, it's not guaranteed actually that it's going to be completely, it's always going to vanish, and it doesn't. This thing picks up again the kind of correct structure for that sort of thing. Okay, now I told you one possibility for how to cancel this anomaly. Are there other ways to do it? So we proposed a term like this. It turns out that there's other ways to do it, which are at some level a little more exotic. But if you were doing this as a condensed matter physicist, you would probably entertain them as well. You can introduce basically inside of the 10D theory a non-invertible topological field theory, quantum field theory, and cancel the anomaly alternatively using a so-called topological Green-Schwarz mechanism. Now, this mechanism in the present context is a bit funny because what it would actually lead to is a different spectrum of stringy objects and backgrounds. So for example, you would find that there's kind of no background you can talk about with type 2B on C2 mod Z3, no S-folds, and other types of things are also kind of excluded. This just has to do with the fact that there's a Gauss's law constraint, which kind of forces certain backgrounds to be trivialized. Okay, so what does that mean? Well, that doesn't sound like the type 2B theory we know. On the other hand, maybe they're just in the swampland and they're inconsistent, but at the level of type 2B supergravity, just being a bottom-up person, it's not totally clear where to figure out where the inconsistency lies. Okay.
I think just that you're cutting in your question.
I'm almost done. So option 2 is that they might connect to the standard 2B theory via domain walls, but then that begs the question: how do you build those domain walls? And I should also say that there's a precedent for this. There's the M theory discrete theta angle, which was found in this paper. So it's not unheard of that there could be these kind of discrete variants kind of lurking in the background of what we think of as kind of conventional supergravity theories. Okay, so that suggests that there might actually be a picture like this, that there's actually some just fine discrete data. We don't know the full list of this, which is kind of enlarging what we usually think of as the standard duality web. Okay, future and conclusions, I'll just wrap up here. I told you about topological constraints, parity anomalies, and 2B duality anomaly in a proposed resolution. For the future, I think it would be very interesting to take the 3D dualities that are known and kind of use this to understand some quantum aspects of spin 7 geometry. I think a big question is, do these variant 2B theories exist? And I think another nice question to ask is, how much can topological structures reconstruct? I have a working paper on this, which is very speculative, but anyway. I think it would be interesting to address how much you can actually go from topology back to kind of the standard physics that we understand. Okay, that's it. Thanks for listening, and I'll stop here.
All right. Thank you very much, Jonathan. There's already a question from Sakura, please.
Hi, Jonathan. Thanks for a nice talk. And so you mentioned there's sort of this intermediate level with the metaplectic group. If you look at sort of the duality anomalies for that, then you get terms in the 10D action topological couplings, which depend on something like, more speaking, d tau over some space-time dependent derivative of the axodilaton. So are some of your terms sort of generalizations of these? It wasn't entirely clear by looking at it.
Yeah. Okay. So I didn't have time to kind of reference. So there was some earlier work done on this by
Savelli,
Gabriel.
Right.
So
I wonder whether some of these terms are basically exactly those, and then there are additional. So I wanted to know which terms were sort of.
So their thing was much more about taking axiodilaton profiles, which might have singularities of various kinds. So one of the features here is that the analysis we're doing is kind of at the level of 2B supergravity. So yes. It's actually not touching the same set of anomalies at that level. So
it's in addition, all of it.
Yeah, so this is in addition. So of course there's that story that they developed, right. But this is kind of on top of that story.
Because that you could also call a duality anomaly, right? Because it's sort of an abstract.
That's right. But for that one, they have a pretty clean answer for what how to get rid of the anomaly.
Okay.
So yeah. So this is on top of their story, if you like. But it's yeah. So we can also compute, for example, in the case of spin NP2 anomalies. But this is even beyond that. Yeah. So.
Thanks.
Wati?
Yeah, thanks, Jonathan. That was a very interesting talk. This idea of like the multiple versions of each theory is quite intriguing. I had a question, maybe you even said this, but I didn't quite follow what you said. When you are doing the 2B story and you go to an 11-dimensional auxiliary theory that the 2B is living on the boundary of, is that 11-dimensional theory at least the standard 11-dimensional supergravity and the low energy? Is it like an exotic version of M theory, or is it straight up M theory? I mean, do you have any idea what that theory is, or does it even have to be a well-defined physical theory?
Well, okay. So first off, it's more like a gapped system. So it's more like it's a much more topological system than that. So we're not trying to demand kind of ordinary like M theory or something like that.
I see. This is like a topological auxiliary theory that
yeah.
you're.
So it's much more in the spirit of what you would do in the so-called like descent relations for an anomaly theory, right? So.
Okay.
So for example, when I say the anomaly polynomial for my favorite field theory is actually living in 2 dimensions more, right? That's the kind of thing that we're talking about here.
Okay, so it's not really a theory; it's a mathematical construction that gives you the anomaly. Yeah, good. It's like the descent.
Yeah, but it's a machine that spits out numbers. Let me put it that way. Now,
I guess the thing that threw me off was you had that. Yeah, okay, good. So that A of M, that's just a topological invariant or something there.
Exactly. So actually,
very interesting.
Well, since you brought it up, though. I will mention that something that I wanted to do for a long time is think about F theory in 12 dimensions as basically having an edge mode, which is the 10D 2B supergravity. So in other words, making the elliptic fiber directions more physical, if you like. This goes in that direction. So in a paper with Tizzano from a few years ago, we speculated on how that might work. I suspect that there's a way to fit this story that I'm telling today with that story, but we haven't succeeded in doing that. But it's very much in that spirit of something that you're raising. Yeah.
Very interesting. Thanks, John.
Okay. The official time is up. I don't know what the organizers think. If maybe Jim or Fabian should first make the announcement, and perhaps then Patrick can ask a question. But I think we should first thank Jonathan again for the beautiful talk.